Okay, so we're going to start our introduction into calculus for AP Physics. This is what we're going to have to jump right into within our first chapter as soon as we get back after our summer break. So we need to be comfortable enough to take a derivative as well as an integral, which are two pretty important concepts in calculus. Here, let me see if I can straighten it up a little bit. Okay, so you can see here, calculus is about rates of change. And there's really two different forms that we're going to look at. Differential calculus, which deals with the derivatives. And graphically, the derivative is the slope of the graph. And the integral is the area that is underneath the curve. And I guess another way to better define an integral, it's an infinite sum. So anytime we are going to take an integral, it's not always using the area under the curve. We will be taking infinite sums of certain values. All right, and I'm going to explain differential calculus to you at this point, and we will get into the integral, which is the area under the curve. We might not get into the infinite sum until that comes about in class. Alright, so we've done derivatives in honors physics, we just never called them that. So what I'm going to do is I'm going to create a few position or just graphs with respect to time. So there's a position time graph axis, there's a velocity time graph axis, and acceleration. Oh, that's time. This is acceleration. Okay. And let's get a graph on there. I'll take my right here. I'm just going to randomly draw some type of shape here. That should look familiar to you. Throw one more in there. Okay, so there's a graph of the position of an object with respect to time. All right, now nothing new from last year that the slope of a position time graph gives us velocity. But let's just write this out. The slope is the change in the y's over the change in the x on the generic axis. So our y-axis is the position. So we have a change in position divided by a change in time. Now we know that that is velocity. And this symbol delta right here, delta stands for a large change. So it's very easy to see when we have a constant slope here. So if we look at this constant slope, if we took a large change in time, so that my delta t is going to go from this time to this time. You can see, I mean, it's a measurable amount of time. You can see it. You're going to have a certain large change in position. Okay, and it works well for a constant slope. Well, what happens when our slope is not constant? So let's look at this first section. We can see that this is a curve. So when looking at the slope of a curve, we really have to look at the tangent lines at certain points. So if we make a point here, we can see that the slope, okay, is pretty steep. Well, the further along we get, let's use solid lines, you can see that the slope becomes less and less steep until it reaches 0. So if we were able to zoom in to one of these points, the change in x, the delta, the distance for the time and the x is going to become infinitely small. So we look at a single point. What we do differently with our notation here is for a small change, continue with the blue, instead of using a capital delta, we'll use a lowercase delta. It looks like a d. So dx dt. Okay, and now this stands for a small change, and it's infinitely small. This right here is called a differential equation, and this is one that we're going to have to be very familiar with. It just stands for that the derivative of position with respect to time is going to give us velocity, and it simply means that the slope of a position time graph is velocity, something that we already know about. So what we can do is we can transfer the information from our position time graph down to our velocity time graph. So we know that we have a positive slope that is decreasing to 0. So we'd have to start at some positive v here and then end at 0 in the same amount of time. So we'd have to go some positive velocity to some 0 velocity. Then you can see here that we have a 0 slope, which means that we have a 0 velocity. So we would, over that time interval, stay at the 0 velocity, and then at this point, let's look at the slope here. It is a negative slope, but that negative slope is decreasing. And whenever it does decrease, we always assume it's going to decrease to 0. So we go from a negative velocity down here, okay, negative velocity to 0 in that time interval. So we'd have to have a slope that comes, and this is like an infinite change. You can connect that or not. And lastly, we have a constant positive slope, which means it's constant positive velocity. So we can draw that in right there. Now the next step is to look at this velocity time graph and determine our acceleration. Now if we again write out our slope equation, the slope for this line is going to be the change, the large change in velocity over a large change in time. Now from physics we know that that is the acceleration. So that acceleration dv dt is going to be another differential equation, basically saying that the derivative of velocity with respect to time is acceleration. Again, basically says that the slope of a velocity time graph gives us acceleration. So we can look at that. So we have a constant negative slope. The slope is acceleration, so we have constant negative slope, which means we have a constant negative acceleration over that time period. Here we have no slope, which means we have no acceleration. Here we have a constant positive slope. So at some positive acceleration value we have a positive slope, and then here again we have our 0 slope. And that's go down. Now there is one step further. We don't really have to deal with this, but we can take the slope of this, and that's going to be the change in acceleration over the change in time, which is actually jerk. That's a funny name, right? The derivative of acceleration with respect to time is jerk. Something to be familiar with, but we're not going to use it very much. Okay, so the graph conversions are the visual representation of what a derivative is. So we are going to now switch gears and look at this in a slightly more mathematical way in another video.